Welcome to this last real section for Chapter 4 in this course. We're going to be talking about combustion reactions. So, combustion is the reaction of any fuel with oxygen. The reaction products are really just waste materials, CO2, H2O, maybe some carbon monoxide, SO2, NO, anything, and HCl. These waste materials typically have to be treated before they can be released to the atmosphere. They're no good. No one's trying to salvage them and sell them. The purpose of this reaction is not to create products. The purpose is to release heat. Now, there's some terminology that's going to be very significant. And first of all, complete combustion. Complete combustion is about what happens to all of the carbon atoms in the fuel. Complete combustion, every carbon atom gets converted to CO2. Sometimes part of those carbon, or all of it even, could be converted to carbon monoxide. That's called partial combustion. We're going to always base our reaction terminology and goal setting and processes so that we have complete combustion. You are going to need to be able to balance your own combustion reactions. And so for a simple hydrocarbon, just N C atoms and M H atoms, the complete combustion reaction can be balanced as shown in this reaction here. Of course, you can do it the old-fashioned way like you learned in chemistry class and come up with a balance on your own. And certainly if the fuel is more complicated than CnHm, you would need to be able to do that. Now, the products of combustion, so in this case the CO2 and H2O, whether it's complete or partial or something that's a combination of those two, the product out of a combustion process will always be called the stack gas or the flue gas, because it's going to go out the stack of your process or out the flue of your furnace. One other really key thing that you need to know is that most of the time the composition of the flue gas will be described on a wet basis or possibly a dry basis. The wet basis composition is the composition that you would normally think of. It includes all the components. A dry composition is what has traditionally been measured. It uses an ORSAT meter, so a dry basis analysis is also known as an ORSAT analysis. So an ORSAT meter, basically you take your flue gas and bubble it through a series of columns, and each one has an aqueous solution in there, and it will absorb out maybe the CO2 or the CO or the SO2, whatever. Unfortunately, the water is always going to be not measured because all of these are aqueous solutions. So it does not measure the presence of water, no matter whether there's a lot or a little bit. So the ORSAT analysis will tell you everything except for H2O. So we want to do an example where we figure out the ORSAT analysis for a particular flue gas. So in this particular case, we have 28% CO2 and 15% carbon monoxide. Now, in this case, if we're trying to do an ORSAT analysis, it means how much do you have without the water. So let's assume a basis (100 moles of stack gas or flue gas. Okay, so that means I have 28 moles of CO2 and 15 moles of CO for a total of 43 moles of dry gas, not water. And so if I want to know the ORSAT analysis, it's simply going to be 28 over 43, which is 65% CO2, and 15 over 43 equals 35% CO. And this would be the ORSAT analysis, or the dry basis analysis. Those two are interchangeable. Another key thing to being able to study combustion reactions is that we frequently are going to talk about excess air. Now, if you look at this diagram up here, we have the ratio of fuel to air. So too much fuel is to the left, too much air is to the right, and exactly the stoichiometric feed is in the center on the shown as the y-axis. Then with that, we can look at how much carbon monoxide is produced in the combustion, how much heat is being created, how much fuel there is, how much oxygen is going to be left at the end. And what we'll see is that there's kind of an area where the amount of heat to amount of fuel used, oxygen consumed, and CO2 or CO is the bad guy, turns out to be kind of in this range. Typically it's about 20% excess oxygen, roughly. Now, we know that fuel costs money and oxygen is free. We would rather produce CO2 than CO, and so therefore we always have the fuel as the limiting reactant. So there's going to always be this key question of how much excess oxygen are you going to have, or if you want to specify it, how much should you add? So theoretical oxygen is the amount of O2 that's going to be required for complete combustion. We design for CO2 production, not CO. Oxygen comes with air, so we usually, instead of talking about theoretical oxygen, we talk about theoretical air. So this is how much air would be required to provide that theoretical oxygen. It's fine if we take 21% oxygen and 79% nitrogen. The molecular mass is going to be 29 grams per mole, pounds per pound mole. We can do a more complete analysis if you wish. Page 143 in the old book. I actually don't know the reference for the new textbook, but you can do a more complete analysis if you'd prefer. So we can calculate the theoretical oxygen, use the proportion of oxygen to nitrogen. That should be N2, not NO2. And we'll just get rid of that O there. And that'll get us the theoretical amount of air we need. And so then if we need excess air, that's how much extra we have in addition to that. It's frequently expressed as a percent. So one thing that's really key to note is that the percent of excess air will always be the same as the percent of excess oxygen. Let's look at one quick example. We're going to do combustion of liquid hexane and liquid heptane. 3 liters of liquid hexane and 4 liters of liquid heptane are burned with 60% excess air, and we want to know how many moles of air will be fed to the burner. So in the appendix of the textbook, there is a data table, it's Appendix B. We're going to start referencing this more and more, so this is really our first time to really need to use this. But I have found in the table the excerpt that's for heptane and hexane. And this data shows the formula, the molecular mass, specific gravity, melting point, enthalpy of melting, boiling point, all sorts of various things that we'll be using as we progress through the course. But in this case, what we need is molecular weight, because that's going to take us from mass to moles, and specific gravity, because that'll take us from liters to mass, so volume to mass. We also are going to need to know the combustion reactions for these. So this is your first opportunity. You might try pausing this and seeing if you can write down the combustion reactions. So C6H14 plus O2 makes CO2 plus H2O. Now we always do this for formation of CO2. And if you calculate the constants, we have those as our stoichiometric coefficients, and for C7H16, we end up with that. Now what I need to know is how much oxygen is required based on these reactions. So I need to know how many moles of each. So I need to figure out the number of moles. So I have 3 liters of C6H14. Okay. The specific gravity of this is 0.659. So that means there are 659 grams per liter. And then the molecular mass, 86.17, 1 mole is 86.17 grams. So I have 22.943 moles of C6H14. We'll do the similar calculation for 4 liters of C7H16. All right, so now then, how much oxygen is going to be required? Well, I'll need 9.5 times as much oxygen as there is C6H14. So 9.5 moles of O2 per 1 mole of C6H14. And 11 moles of oxygen per 1 mole of C7H16. Well, I didn't write the individual results down, but the total amount required will be 518.3179 moles of O2. Now that's how much is the theoretical O2, so the required O2. How much air is required? Well, I'm going to take my answer for every 1 mole of air, there's 0.21 moles of O2, meaning that I need 2,468.1805 moles of air. This is the required air. What's the actual air? Well, I have 60% excess air. So I have the 100% I need plus the extra 60% times 2468.1805 moles of air. Therefore, I need 3,949.0888 moles of air. Now, using appropriate sig figs, remember they just gave me 3 liters and 4 liters, then I would say that I need 4,000 moles of air. Okay, so that shows you a little bit of how to calculate using theoretical air, doing the balances for complete combustion, and then also a reminder about the use of proper sig figs.